few days ago, we looked at position time graphs, the shapes of position time graphs and what those shapes described. And then we looked at the analysis of position time graphs, determining values of position or velocity or whatever the case may be from those position time graphs. Today we're going to do something real similar with velocity time graphs. You can see 5 different shapes of velocity time graphs up on the board right now. They correspond to the exact same 5 shapes you saw for position time graphs, but all 5 of them have different meanings than position time graphs. Why? Because the y-axis is different. The responding variable is velocity as opposed to position. What I want to do now is go through these 5 shapes, compare the meaning on a position time graph that had that shape with the meaning of the velocity time graph that we see in front of us right now that has that shape. So let's look at the first one here. Velocity versus time. It's a straight line. If this was a position versus time graph that was a straight line, it would mean a constant velocity, a constant positive velocity. I'll tell you right now, it doesn't mean that for velocity time. How do you know that? Well, because you can clearly see that the velocity is changing. So what does it mean on a velocity time graph? Constant velocity for position time, but what does it mean for velocity time graph? Yep. Good. It's a constant or a uniform acceleration. Usually you use the word uniform there as opposed to constant, but if you wrote down constant, I'd mark that right. It means the acceleration is not changing. The velocity is, it's speeding up, but it's changing at a constant rate. It's kind of like putting your foot on the gas pedal of your car, not putting it down further, not pulling it back. You're keeping your foot on the gas pedal in the same place, so you accelerate at a constant rate. What's the next one mean? Velocity versus time, if it's a straight horizontal line. If this was a position time graph, it would mean the object is stopped. It isn't stopped here because the velocity isn't 0. So what does this one mean? Steady, what do you mean by that? Not changing? Yeah, keep going. Yes, good. It's a constant velocity. The velocity of the speed is not changing, right? Look at this. We don't have any numbers on the y-axis here, so I can't tell you what the velocity is, but I do know that the velocity rate here is exactly the same as the velocity here, here, and here. It's a constant velocity. As opposed to an object being stopped. What about the third one? Straight line, but sloping downwards this time. If this was a position time graph, it would mean a constant negative velocity. It's not what it means this time. Oliver?
And the acceleration is slowing down, so it's coming to a stop.
It is coming to a stop, but be careful with what you said there. The acceleration is not slowing down. The velocity is decreasing. The velocity is slowing down. It's a constant acceleration, right? It's a uniform acceleration. It's a uniform negative acceleration. And a uniform negative acceleration in this case means deceleration. A uniform deceleration. We got a velocity time graph that's curving upwards. If this was a position time graph, it would be acceleration. Well, it still is. But this isn't a constant acceleration. This is an increasing acceleration. So not only is your velocity increasing, but the rate at which the velocity increases. This is like putting your foot on the accelerator of the car just a little bit. What happens when you put your foot on the accelerator? You speed up, right? But then you put your foot further and further and further down. You push down more and more and more and more until eventually your foot's on the floor. As you push your foot down more and more on the accelerator, not only do you speed up, but the rate at which you speed up increases. That's what's going on here. Finally, the last one, well, the second to last one, because I'm going to draw one for you as well. If this was a position time graph, it would mean deceleration. That's not what it means here. The velocity is increasing. Look, here's a velocity that's a small value. Here's a bigger velocity. Here's a bigger velocity. Here's a bigger velocity. Here's a bigger velocity. It's accelerating, right? It's not slowing down, it's speeding up. But the rate at which it speeds up decreases. Does that make sense? How quickly, here's a kind of a mouthful or an earful to interpret this. The rate at which the velocity decreases, sorry, the rate at which the velocity increases, decreases. Does that make sense what I just said? The velocity increases, but the rate is decreasing. That's like putting your foot on the accelerator right down to the floor, and then you kind of let off, right? You're still speeding up, but you're not speeding up as quickly as you were before. The rate at which the acceleration, sorry, the rate at which the velocity increases, decreases. We'll call it a decreasing acceleration. And there's one more that I wanted to give you here. We've got velocity versus time again. And this time the shape, it's going to look similar to what we see up there, right above it. In the first stage of this, from dot to dot, it's a uniform deceleration. It's slowing down. Look, the velocity is a certain value here. Oh, it's smaller, it's smaller, it's smaller, it's smaller. What happens right here? Yeah. Well, specifically at this point, it stops. And then it starts moving backwards. Now it starts moving in the negative direction, right? What's happening to its velocity, though, in the negative direction? Velocity is getting bigger, isn't it? So it's speeding up in the negative direction. Here it's slowing down in the positive direction. Here it's speeding up in the negative direction. Make sense? Accelerating in the negative direction. So what do we do if we want to find some values from these graphs now, more than interpreting the shapes of them and what they all mean, acceleration, constant velocity, whatever? What if we want to find some values? We can find many of the same things on these graphs as we found for position time graphs, but of course we're going to find them in a different way. How would we go about finding the instantaneous velocity on a velocity time graph? Well, you might remember that on a position time graph, where we wanted to find position, we went up and over. I told you, whenever you want to find something that's on the y-axis of the graph, go up and over. Here we want to find the velocity on a velocity time graph. So let's go up and over. Wherever the time is that you want to find the instantaneous velocity, just go up and over. And of course, if you want to find the change in velocity, you're going to find VF and VI and subtract them. So go up and over times 2, up and over, and then you're going to subtract. I get 2 velocities, subtract the 2 of them. So you can see that this one kind of leads into this one, right? Next one, finding the acceleration. Well, the acceleration is delta V over delta T. Delta V is what we just found, the change in velocity. So this one is going to lead into this one. You can get the velocity by going up and over. You can get the change by doing it twice and subtracting. You can get the acceleration by taking that value and dividing by time. The displacement, ooh, this is where it's different. This is unlike anything you did for position time graphs. To find the displacement on a position time graph, it's easy. You just go position final minus position initial. On a velocity time graph, it's harder. On a velocity time graph, you have to break it up into recognizable shapes and find the area of those shapes, and then add them up. It's the area between the line and the x-axis. So if you happen to have a graph like this, that's the area you're looking for. If you happen to have a graph like this, then this would be the area you're looking for. the area between the line and the x-axis. If it's above the x-axis, it's positive. If it's below the x-axis, it's negative. Take all the areas that you find, add them up, that gives you your displacement. Sometimes it's one simple shape that you can find the area of. Sometimes it's 4 or 5 different shapes that you've broken it down into. Not harder then, just a little bit more work, that's all. Now there's one more thing that I haven't asked you here, but it's not that hard. The average velocity. The velocity is changing, but we can still find an average velocity. The average velocity is displacement divided by time. So once again, look, we've just found displacement. So one leads into the next. Get the area divided by the total time. All right, let's take a look at the example that's on the front side of your worksheet. The first question says, what's the velocity of the object at 4 seconds? We know what to do there, right? What do we do? What do we do there? Yeah, up and over. 4 seconds, we go up, over, looks to be 15 meters per second. Okay, that's easy enough. What's the change in velocity over the entire graph? Well, we go up and over, and subtract it. So the final, it looks to be 33 meters per second. The initial looks to be 3 meters per second. So the change in velocity would be 30 meters per second. The acceleration is the change in velocity over the time. We just found the change in velocity. It's 30 meters per second, and the time is 10 seconds. So the acceleration will be 3.0 meters per second squared. The displacement, this one's a bit harder, right? The displacement, we break it up into our shapes. It'd be nice if we just had one simple shape there, but we don't. Notice that because that doesn't intersect with the origin, we have to draw a triangle right here. I'll call that area 1, and a rectangle right here we'll call area 2. The area of the triangle is 1/2 base times height because that's the area of any triangle. The base is 10. The height goes from 3 to 33. The height is 30. One half of 10 times 30 gives me 150 meters. And the area of the rectangle down below is base times height, or length times width. Base is 10. Height goes from 0 to 3. The total displacement would be 180 meters. Just add them up. And finally, you're not asked this, but you could be, the average velocity. Let's take the displacement that we just found, 180 meters, divide it by 10 seconds, gives me 18 meters per second. Is that all right? I don't think anything we've done here today is crazy hard. This area thing is a little bit tricky, and sometimes it's hard to remember some of the things, but it's not crazy hard conceptually. What becomes difficult is when you start seeing position time graphs and velocity time graphs kind of mixed up. So one day you get a position time graph, the next day you get a velocity time graph, the next day you get a position time graph again. People tend to mix them up. People tend to try to find the area on a position time graph. We don't do that. Okay, people remember to find the area. They just do it in the wrong place. Be conscious of that. Be careful of that. And you should have some success here. All right, here's what I'd like you to work on. In addition to those check and reflect questions from your textbook, okay, over the break, you have those 14 questions and this worksheet if you don't get this worksheet finished in class today, the 4 questions on there. All right, that's it.